Imagine your nervous system as a high speed fiber optic network. Signals fly from your brain to your muscles at speed up to 120 meters per second. But how does an uninsulated cell membrane move electrical signals that fast without leaking energy? The answer lies in a brilliant piece of biological engineering called as saltatory conduction. But what happens when that system breaks down? Let's look at it. Now take a look at the upper diagram in this image. This represents a healthy, normally myelinated nerve fiber. Those yellow block-like structures wrapped around the central axon are the myelin sheath. Think of myelin sheath as high-grade electrical tape. It provides high electrical resistance and low capacitance, which essentially means it prevents electricity from leaking out of the sides of the axons. Because the myelin tightly insulates these segments, the electrical signal cannot travel continuously down the membrane. Instead, it is forced to jump. Notice the gap between the yellow blocks. Those are nodes of Ranvier. These nodes are packed with voltage gated sodium channels. As shown by the red area on the left, that's where the action potential currently sits. The broken arrows represent the local circuit currents. Following ahead, because the myelinated segment resists current leakage, the action current is cleanly directed straight to the node of Ranvier. The signal literally leaps from one node to the another. This is saltatory conduction. It is lightning fast, energy efficient, and incredibly reliable. Now let's look at the lower diagram, which shows a demyelinating region. This is the hallmark pathophysiology of demyelinating diseases. Notice the rough, degraded, pinkish brown section where the myelin has been stripped away, leaving the bare axon exposed to the extracellular environment. When myelin is destroyed, two major physical parameters completely change. The first one, the insulation is lost, meaning membrane resistance plummets. Second one, capacitance increases, meaning bare membrane now stores electrical charge rather than letting it pass on. Look closely at the broken arrows. In this lower section, instead of a single efficient current jumping cleanly to the next healthy node, the electrical current gets short circuited. The current leaks out through the damaged, denuded region of the axon. Because the current is bleeding into the surrounding tissue, the electrical amplitude drops drastically. By the time it reaches next intact node, the voltage is too weak to hit the threshold required to fire a new action potential. As the caption explicitly notes, further propagation of the action potential is completely blocked. This exact microscopic failure is what happens and is what explains the clinical symptoms seen in the patients. When millions of these microscopic short circuits happen simultaneously in the central nervous system, signal gets delayed or may be entirely lost. This manifests as the muscle weakness or vision loss or paresthesias, characteristic of conditions like multiple sclerosis. The nervous system is an absolute masterpiece of bioelectricity. But as this image beautifully illustrates, even the fastest superhighways fail if you lose the insulation.